Okay, so last time we were together, I talked about carbon compounds and why carbon is so important to biological organisms. Um, One of the things that makes carbon so important is its ability to make basically large, complicated molecules that have lots and lots and lots of things on them. Um, and we called those things functional groups, and those functional groups are typically hanging off of what's called the carbon backbone, which is sort of like, a Christmas tree, and then the functional groups are all of the ornaments hanging off of it. Now, you could make very large and complicated organic structures, but your body doesn't have time to build everything custom, right? Your body doesn't have time to build, uh, you know, 50,000 different, completely unique organic molecules, each uber specialized to a particular task. It would be sort of like if every building in the world was uniquely carved out of, granite. Yes, it could theoretically be done, but it would be a huge amount of work. And so, what we do typically when we want to build something is we have standard components. There are many, many different types of houses, but they are all built out of basically the same things. You've got, wooden 2x4s of various lengths. You've got wall paneling. Um, you've got roofing tiles, and you have a few different types of each of these things, and you can put them together in a whole bunch of different ways. They're basically like Lego blocks. You could have maybe just, I don't know, 10 or 20 different types of Lego blocks. You've got like your standard 8 Lego brick. Then you've got your flat Lego brick, and then you've got your half Lego brick, and a few specialized pieces. And from those, you can build like pretty much anything you want. Your body uses basically the same trick. It has really only 4 different types of what we call biological macromolecules that it uses on a regular basis. And those macromolecules, or at least 3 of the 4 of those macromolecules, are what we call biopolymers. So proteins is one of them, but your body doesn't just have one protein. Your body has tens of thousands, potentially hundreds of thousands of different proteins that it uses. All of those proteins are large organic macromolecules. They are all biopolymers, but they are all different. And even though they're all different, they're all made from basically the same pieces, the same basic bricks. They are what is called a polymer. So poly means many, mer means thing, repeating unit. Polymers are made from monomers. Mono means one thing. A monomer is your basic building block, your Lego, as it were. The polymer is the thing that you are building out of the Legos. And every different biopolymer has different monomers and has different ways that it is put together, and has different types of monomers. But all 4 of the biological macromolecules are biopolymers. 3 of them have more of an interesting polymer structure than the others. Polymers are repeated sequences made with a repetitive series of identical or similar, typically similar, subunits called monomers. These all have a similar basic structure, but will have different functional groups hanging off of them. So, for an example, starch. We all know starch. Starch is what you find in potatoes and what you find in rice and grains and bread and everything like that. Delicious stuff. Well, starch is a polymer, and it is a polymer of glucose. So it's basically a bunch of glucose monomers all stuck together, about 3,000 of them. Polymerization is the process of joining monomers to form polymers. And I'm going to give you an example of polymerization here. So, generally speaking, polymerization is driven by what is called dehydration synthesis. Dehydration means to remove water. And that's literally chemically what you're doing. When you polymerize things, you usually have two monomers. And these two monomers will have usually an OH. That's a hydroxyl subunit. Both of them will have a hydroxyl subunit. And through various types of chemistries, which we won't get into here, but which you'll probably get into when you take organic chemistry, you remove an H from one of those and an OH from the other. That's HOH, H2O. These leave as water. They combine and they leave. And the energy of that water leaving, because water is very stable, so water likes to form, the energy of that water leaving is what's going to drive the polymerization. So now you see that this dimer, a dimer is a polymer made of two monomers. This dimer is now connected with this oxygen linker here. And now that oxygen is connecting to both of these monomers, linking them together. They have now been polymerized. One of the cool things about polymerization, I'm going to show you an example here. So what you're seeing here is a glucose molecule. Glucose is a 6-carbon sugar, and it's in this ring structure that's got kind of bendy ends like this, right? So this is glucose. Each of these junctions here is a carbon. You can see that this glucose has a bunch of OHs coming off of it. If we have more than one glucose, right, coming in together, so here we have a second glucose, we are going to polymerize them by dehydration. Keep an eye on these two groups here. You see that the water has left, that H2O, and we now have these two glucoses connected together. Two glucoses connected together, by the way, is called maltose. Maltose. My pen doesn't seem to be working very well, but maltose right there. This is what would be called a disaccharide. A sugar made of just a monomer is called a monosaccharide. A sugar made of two monomers is called a disaccharide. When you get longer than two, it's usually called a polysaccharide. Probably the most famous disaccharide is sucrose. which is table sugar, and that is a glucose hooked up to a fructose, which is a different type of sugar. This is two glucoses hooked together. One of the really cool things about polymers is that, just like Legos, you can take your Lego blocks and you can put them together to build a castle, right? And then if you get tired of the castle, you can take your Lego blocks apart and, reuse them in a different configuration to make a spaceship or something like that. And you don't have to destroy the Lego blocks. You can just snap them together and then take them apart. And you can do the same thing with polymers. So here we have a dimer, a 2-mer, and what we're going to do is we're just going to break this dimer apart back into monomers. Remember, we use dehydration synthesis to put them together. So we took a water away to put them together. What do you think we're going to add to break them apart? We're going to put a water back in. So we're going to use water to cut the dimer apart, right? This is called hydrolysis, right? Hydro means water, and so this is water. And lysis means to cut. So literally this means cutting with water. We're using water to cut this molecule apart. Pay attention to this term. Hydrolysis is a term that we are going to be using a lot in this class. Remember that what that means is that we're breaking down a polymer by cutting it with water. So just to show you depolymerization with hydrolysis, we've got our maltose right here. And this is a carbohydrate. It's a polymer carbohydrate. It's a disaccharide. We have our water comes in, and then usually an enzyme is going to take this water, split it into the H and the OH, and then use the energy of that splitting to cut the molecule apart. And now we have two individual glucose monomers, and these could, for instance, be combined with a fructose to make sucrose or something else. You could make something else with them if you want. This polymerization and depolymerization is the way that your body builds the chemicals that it is made out of. It is one of the most essential reactions in the body, and it's going on all the time.